All right, let's dive into something pretty cool today. Distributed Object-Oriented Database Management Systems. Yeah, I know, it's a total mouthful. But the idea behind it is actually pretty intuitive. It's all about how we manage data that's as messy and connected as the real world.
I mean, think about it. Your classic database, it's awesome for things that fit neatly into tables with rows and columns. But what about something like a car? It's got an engine, wheels, a full service history. Or what about a person and all their relationships? That kind of stuff just doesn't cram nicely into a spreadsheet. And that, right there, is the exact problem these object-oriented databases were built to solve.
So here's how we're going to break it all down. First, we'll look at the main idea, mashing up software objects with distributed networks. Then, we'll dig into the 4 big principles of object-oriented programming that make it all possible. After that, we'll see why spreading this data out is such a game changer, how these systems are actually designed, and finally, we'll take a quick look at the different ways they're built. Let's jump in.
When you strip it all down, this entire concept is really just a marriage of 2 massive ideas. On one hand, you've got the super clever model of object-oriented programming, and on the other, you have the brute strength and flexibility of distributed processing.
And this is really the magic of it, right? The object-oriented part lets us build these rich digital versions of real-world things. We can capture not just what they are, their state, but also what they can do, their behavior. Then, the distributed side takes that powerful model and stretches it across a whole network of computers, giving it incredible scale, speed, and making it way more robust.
Okay, but to really get how this works, we need to understand the blueprint they use to structure all this real-world data. It all boils down to what are called the 4 pillars of object-oriented programming. Let's walk through them.
First up is encapsulation. You can think of this like a protective little capsule. An object bundles its private data, its internal state, together with the public functions or methods that are allowed to change it. This is so important for keeping things secure and predictable. It basically means every object is the master of its own data.
This Sims cat example is perfect. Imagine a cat in a game. Its mood, its hunger level, its energy, that's all its private state. You, as the player, can't just go in and manually set hungry to 0. Nope. You have to use the public methods the game gives you. You can feed it, play with it, or let it sleep. That is encapsulation in a nutshell. The cat object is in complete control of its own state. So once you've bundled everything up in that capsule, the next logical step is abstraction. This is all about hiding the messy, complex details on the inside and just showing a simple, clean interface to the outside world.
A coffee machine is the perfect analogy here. You don't need to know anything about heating elements or water pressure to make a cup of coffee. You just need to know where the beans go and which button to press. Abstraction lets us use incredibly complex things without needing an engineering degree.
Our third pillar is inheritance, and this one is all about being efficient and organized. The idea is, instead of building every new object from scratch, you can have a new child class automatically get all the features and behaviors of an existing parent class.
Check out this vehicle-to-car example. We can have a general vehicle object that has properties like an engine, a make, and a model. Then we can create a car object that inherits all of that automatically. But the car can also add its own special things, like bumpers or a passenger capacity. A car is a vehicle, just a more specific type. It's a huge time saver. And the 4th pillar, polymorphism, just builds on this idea. It lets you use a single command, like drive, to work on lots of different objects, whether it's a car or a truck.
Okay, so we've got this really smart way to model data. But why go through all the trouble of spreading these objects across a whole network of computers? What's the big payoff?
Well, the advantages are huge. The biggest one is called transparency. The system hides all the complicated, messy details of where the data lives. For example, you don't have to know if a customer's data is stored in a server in London or one in Tokyo. That's location transparency. And if there are 5 backup copies of that data, you just interact with it like there's only one. That's replication transparency. All of this leads to a system that's way more reliable and gets a massive performance boost. Distributing things also lets us be smarter about how we get work done. A flat transaction is simple. One thing happens, then the next. But a nested transaction is much cooler. It breaks a big job into smaller pieces that can all run at the same time. Not only is this faster, but if one of those small pieces fails, you might only have to fix that one little bit, not start the whole job over. It's just a much more resilient way to operate. So, how do you actually go about building one of these things? Where do you even start? Well, like any good architect, you start with the blueprint, deciding how to break up your data and where to put it.
And that first big decision is called fragmentation. This is basically the art and science of slicing up a big collection of objects into smaller, logical chunks. And you don't just do it randomly. You do it strategically to make everything faster and more available.
There are two main ways you can slice it. Horizontal fragmentation is like splitting a spreadsheet by its rows. You could, for example, put all the employee objects from your Boston office on a server located in Boston, and all the Paris employees on a server in Paris. Then there's vertical fragmentation, which is like splitting a spreadsheet by its columns. You might put a student's basic registration info in one chunk, since it's used all the time, and their fee details in another, since only the accounting department needs that. Here's a great visual of that. This project table is being split horizontally, based on location. So all the projects in Montreal and New York are in one piece, and the Paris projects are in another. Now think about it. If someone in the Paris office runs a report on local projects, the database only has to search that one small local piece. It's way faster. All right, so you've fragmented your data. Now you need a system for your applications, the clients, to actually talk to the database servers. And this is where we get into the different architectural models.
You've really got two main flavors here. In an object server model, the server is the smart one. The client asks for a specific object, and the server does all the hard work, finding it, putting it together, and sending a perfect, ready-to-use object back. But in a page server model, the server is more like a simple librarian. The client asks for an object, but the server just figures out which physical page on the disk that data is on, grabs that entire page, and sends it over. It's then up to the client to find the object it needs inside that page. It's a classic trade-off. Do you want a smart server and a simple client, or a simple server and a smart client?
You can see that flow right here in the object server model. The client just makes a request, and the server handles all the heavy lifting. It processes the query, manages everything, and sends back a nice, clean object. The server is definitely doing most of the work here.
Now contrast that with the page server. See how the logic is more split? The server's main job is just to grab pages off the disk. The client has to have its own object manager to handle the rest. This really highlights that trade-off between having a heavy client versus a heavy server.
So to put this all into perspective, where does an ODBMS fit in the grand scheme of things? This table really clarifies the difference between what we've been talking about and its close cousin, the Object Relational Database, or ORDBMS. And the biggest difference is right there in that first row. A true ODBMS stores data as objects, from the ground up. An ORDBMS is more of a hybrid. It's a traditional table-based database with some object features bolted on. Which really brings us back to our big final question. We started this by asking how you can possibly model a world that doesn't fit into a neat spreadsheet. We've just walked through a pretty powerful blueprint for how to do exactly that. So as our world gets even more digital, more complex, and more connected, you have to wonder, right? Are these the core ideas that will shape the future of how we manage all data? Definitely something to think about. Thanks for taking this deep dive with me.